Welcome back, guys. What you're looking at here is the final project pulse model, and the chart comparing nameplate AC versus usable AC energy explains why today's lesson is critical. The dashed red line is the nameplate AC energy, what the market and the contracts expect the battery to deliver. The blue area is the actual usable AC energy, and the orange line is the effective duration in hours. Notice what happens around year 2038. Due to degradation effects, usable energy and duration drop almost below nameplate. You can see our nameplate duration and AC nameplate energy on the left-hand side of the dashboard. In year 2038, the battery's degradation is about to hit commercial limits. And right before the BESS is about to breach nameplate values, when the curve jumps back up in 2039, that's augmentation. New battery cells are installed to restore nameplate performance. The key point is this: whether you need one augmentation or two over 20 years depends entirely on the revenue structure. A fully merchant case like case 12 degrades much faster and requires two augmentations. A fully contracted tolling case like case 1 will likely only need one augmentation. In this lesson, we will build the exact mechanics that determine this curve, how DC energy turns into AC deliverable energy, and how effective duration is calculated year by year. And in the upcoming lesson, we will use the duration breach that we determine in this lesson to trigger and size the actual augmentation event. Now let's move back into Excel where we have left off at the end of the last lesson. Welcome back to where we left off in the previous lesson. If you're new to this series, I recommend starting with Deal Lab Part 1, where you can download the model start file for free and build everything step by step alongside me. In the last lesson, we built the first half of the capacity logic. From AC at the grid down to usable DC energy in the battery. We accounted for availability, curtailment, efficiencies, and degradation, and we ended with total usable DC energy per cycle. In this lesson, we will do the second half of the journey. We will take that usable DC energy, convert it back to AC at the point of interconnection, and work out the actual AC deliverable energy per cycle and the effective duration in hours. And we will skip the detailed augmentation blocks for now. Rows on augmentation 1 and 2 and the augmentation trigger test will be covered in the next lesson. For this lesson, our goal is simple. How many megawatt hours can the BESS actually deliver at the point of interconnection each cycle, and what duration does that translate into? To set the scene, let's quickly jump back to our system diagram and remind ourselves how the battery, inverter, and grid fit together. Let's zoom out for a moment and see where today's calculations sit in a real system. On the left, the distribution grid delivers AC power at 50 or 60 Hz. Before the battery can interact with it, a transformer steps the voltage down to the level required by the power conversion system. The power conversion system, or PCS, is a bidirectional inverter. In the charging direction, it takes grid synchronized AC or alternating current and converts it into DC or direct current, so the battery can store energy. That's the part we effectively captured in the previous lesson when we modeled efficiencies and DC energy inside the BESS. In discharge mode, the process runs in reverse. The power conversion system takes the battery's DC energy, pushes it back into the transformer, which then sends clean, grid-synchronized AC back to the grid. On the modeling side, what we're going to do now is represent this discharge path numerically. Start from usable DC energy, pass it through the DC to AC efficiency chain, cap it at the point of interconnection nameplate energy, and express the result as an effective and deliverable duration. With that picture in mind, let's hop back into Excel and implement it. Alright, let's get to the actual modeling part of this lesson. The first block here, AC to DC conversion, takes us from usable DC energy inside the battery back to the point of interconnection in AC terms. And to model the second part of this energy journey, we first need to hop into K99 and determine our usable DC energy per cycle. And this is going to be a very simple linkage to our previous row that we have already calculated in our previous lesson, which is row 96. So hit enter and drag this one over, Control R. And as you can see, for now, the usable energy per cycle in the block up here only considers our initial BESS. In the next lesson, we will also implement our two augmentations. But for now, the initial BESS just degrades without scheduling any further augmentations. And to get from our usable DC energy within our BESS back to the point of interconnection at the grid, what we'll have to do is apply two losses. So we take K99 and multiply it with open parentheses, scroll up, our two discharge efficiencies and losses. So that is row 38 and row 40. So we pick up row 38 and multiply this also with row 40. These are the same losses we have applied in the previous lesson on the charge path, but now we consider the same values for the discharge path. Close parentheses, hit enter. Let's drag that one over to the right, Control R. And what you can see here is that initially we took in row 63 521 megawatt hours AC from the grid, converted that AC energy into usable DC energy within the BESS, and upon discharge we deliver 481 megawatt hours on an AC basis back to the grid. So effectively, we lose about 40 megawatt hours through the charging and discharging path. Okay, now let's move on to the next block. In this block, we make sure that we don't dispatch more energy than the point of interconnection rating allows. We calculate the maximum AC energy the plant could deliver per cycle purely from its nameplate. And the first thing we will have to do is pull in our point of interconnection nameplate AC energy per cycle, which we have already calculated in our previous lesson here in row 59. And row 59 essentially reflects our contractual obligations, where we have to deliver 200 megawatt AC gross power at the point of interconnection for a duration of 2 hours when we select case 1. So the nameplate AC energy is the gross power times duration. 200 times 2 is 400. And here we do a simple linkage to this value of 400 megawatt hours AC. Drag this one over, Control R. And in the next row, we have our usable energy after DC to AC conversion, which is again a simple linkage of what we have just calculated in row 100. Drag this one over, Control R. And now these two rows represent two different things. Row 103 basically represents our contractual obligation. In the tolling agreement, we will have to deliver 400 megawatt hours AC per cycle, whilst row 104 reflects the actual physical energy we could deliver. And you can see that in the first year, we could deliver about 20% more energy, while in year 2041, there would be already a breach due to the degradation effect of the batteries. So physically, we could only deliver 396 megawatt hours on an AC basis, while contractually, we will be obliged to deliver 400 megawatt hours. So what we'll do here is have a min formula, and we just take the minimum of the two, of our contractual obligation and our physical capability of delivering this energy. Drag this over, Control R. And we will see that from year 2026 until year 2040, we will fulfill our contractual obligation of delivering 400 megawatt hours on an AC basis. However, in year 2041 onwards, we would breach that obligation. And to avoid any breach in obligations, this is where the augmentation will come into play in our next lesson. And now that we have determined the physical energy that we can deliver back to the point of interconnection, we can calculate the effective duration. And we will use an if-error statement here because we will divide by 0 in our first year. So if-error. And we will take our usable energy after DC to AC conversion in row 100 and divide this by, let's scroll up, our actual gross power at the point of interconnection in row 46. Hit F4 2 times, and if this is an error, we want it is 0, otherwise the initial value will be returned. Hit enter. And we can drag that formula down, so let's go in row 109, hit Ctrl D, hit F2, and this time for the deliverable duration, which is capped, we will actually link this to row 105, where we take the minimum of the physical boundaries and the contractual obligations. Hit enter, drag that over to the right, Ctrl R. And the story is the same as in row 105. We again sustain our contractual obligation of 2 hours of duration for the first 15 years. During which our actual physical duration or our effective duration actually has quite some significant headroom initially, which degrades over time, and eventually in year 2041 we would fall below our 2-hour contractual obligation regarding duration. This cap duration is what we'll feed into the augmentation trigger logic down here in the next lesson, where we'll test when effective duration falls below our target and then size augmentation campaigns to restore that headroom. Alright guys, I will see you in the next lesson. See you there.